So, let us start. Under steady incompressible flow conditions, so mass balance and the momentum equation applied to a control volume So, we looked at two types of examples. One is internal flow and the other is external flow. So, in the external flow problem, interest was in finding the force acting on the object. The object is kept inside the flow field. So, this was the flow configuration. There was an object inside. Now, we have discussed the application of the mass and momentum equations when the control volume is filled with the fluid. So, in a problem of this type where you have a solid object inside, we create a multiply connected domain. That means, you have an outer control surface. This is the outer control surface and you have an inner control surface. So, this inner control surface just envelops the object and we apply the boundary condition u dot n equal to 0 over the solid surface. Now, when you carry out the calculations, you will get the force acting on the control volume. Under what conditions will it be equal to the force or equal and opposite to the force acting on the control surface. So, for that the side boundaries are taken to be the far field. So, the implication, for example, let us name this 1, 2, 3, 4. So, the side boundaries would be 3, 4, 1, 2. These are side boundaries. So, these were picked from a convenience viewpoint. So, that here the x component of velocity I think I labeled it ABCD last time. So, let us make it ABCD again. And this is inflow plane 1, outflow plane 2, 3 and 4. So, u3, u4, these are the x components of velocity on surfaces 3 and 4 are practically equal to u1. Okay. u1 is the undisturbed flow coming in. So, the side bound, so this helped us in the evaluation of the integral. The other implication of u3, u4 being close to u1 is that the velocity distribution in that region is nearly flat. Okay. So, let us draw the velocity distribution on plane 1. This is u1 coming in. Now, because of the blockage on the outflow plane, you will have a reduction in velocity just downstream of the object. So, pick the side boundaries so that okay. Something like that. So, there is a reduction in velocity just downstream of the object, and velocity becomes nearly constant as you approach the side boundaries. So, see the velocity, if the velocity becomes nearly constant away from the object, as you can see, what can you conclude about the gradient in velocity? The gradient in velocity in that direction is 0. Therefore, shear stresses are 0. So, the far field boundaries are selected in such a way that shear stresses are 0 on these surfaces. So, the average of this velocity distribution is u2. Now, the difference in velocity, difference in u1 and u2 will leave from the side. So, you will have some y component velocity, this is v4 and similarly v3, and the average of that is v4. There is a distribution v3, v4, average is v3 and v4. Okay. That is what went into the integral evaluation. Now, if the downstream plane is also somewhat far away from the object is here. Then in an external flow field, you can anticipate pressure to recover, because it is the atmospheric pressure. You have an object here flow, after some time atmospheric pressure is re-established. So, then P1, here you have a distribution P1, here you have a distribution P2, and if it is the far field, it will be nearly equal to P1. Okay. So, no shear stresses on the side walls and the pressure difference in the flow direction is also small. Therefore, the external force, what can you conclude? The external force is localized on the object. The force you have calculated through the momentum equation, that force acts on the control surface enclosing the object, and equal and opposite will act on the object. So, the choice of the control volume helps you in concluding that the force you have found is really the force acting on the object. Suppose you pick your control volume to be very close to the object. Can you write these governing equations? Yes, except that stresses on those surfaces will not be small. So, sum total of stresses acting on the control surface and the force acting on the object, everything together will give you the force you have estimated from the momentum equation. But if you choose the surface to be far away from the object, then the far field condition makes shear stresses 0 on the side walls and pressure drop in the flow direction equal to nearly 0. Therefore, all the external force will be equal to the force acting on the control surface enclosing the object. So, just to rewrite the result we got last time, so we got this result that f x is equal to rho times what was it, u 2 minus u 1 multiplied by u 2 times some h, where this or a 1, I do not remember what symbol was used. Let us say h is this cross dimension. Do you have this result in your notes? Let me confirm. Yeah. Okay, so now this is the result, and then we reasoned out that u 2 has to be less than u 1 because flow is being blocked by the object. Therefore, f x is negative. Gives you the result that f x is negative. Therefore, force, this is force on C v. Therefore, force on object is greater than 0. So, you will write the force on the object as rho times u 1 minus u 2 times u 2 h. So, that looks like an unbalanced force if you think of a chimney and then there is some force acting on it. So, you have to hold it firm at the base. Okay, so, there is a force acting on the object that keeps it in position. So, there are three forces now. One is the force acting on the C v. Next is an equal and opposite force acting on the object. And third is the force required to keep the object in place, which is now equal to the force acting on the C v. So, because of this equality now holds only when you take the side walls to be the side boundaries. You construct the C v appropriately, so that the side walls are far field undisturbed. So, let us say this is P 1 and this is P 2, and suppose P 1 is not equal to P 2, then you will have to write the force acting on the control volume localized on the object plus P 1 minus P 2 h. Will be equal to rho u 2 minus u 1 u 2 h. So, now You could have written F x, but that is the total force acting on the control volume, but when you write it in this form, this is the force acting on the control surface enclosing the object. And if you think the side wall shear stresses are not negligible, then you have to put one more term. That will be shear stresses on the side wall multiplied by the surface area. Now, these calculations are being done on a unit distance normal to the plane of the blackboard. So, force will have units of Newton per meter. Okay, so, if you choose your control volume so that P 1 is equal to P 2, then you will have all the force acting on the control surface, this inner control surface, equal to rho u 2 minus u 1 u 2 h. Okay. Now, this result appears as if it depends on the dimensions of the control surface. You can see this h gives an impression that the calculation depends on the choice of the control volume. Of course, it depends on it because you want the far field conditions to be applied. So, if I make h larger, will f x become larger? So, you can have a quick kind of a response to it, but you will realize that as h increases, this u 2 minus u 1 will decrease. So, more or less u 2 minus u 1 times h will be nearly constant. So, it does not depend on the choice of h. Okay. Now, this approach, so let us note this approach is often used in measurements to estimate the force. So, if you think of force measurement in solids, let us say a spring, you apply force and you want to measure force, what do? You apply it on the spring and measure the displacement times some property of the material gives you the external force. So, force is often measured through its response from a standard material. So, spring is like a standard material with a known stiffness. So, in case of fluid flow, force here in this approach is estimated through the velocity deficit, and the fluid property that is relevant here is density. Okay. So, this is a measurement approach to finding, you may call it fluid dynamic or aerodynamic, hydrodynamic, these are all equivalent terms for finding. It is a measurement approach for finding fluid dynamic forces in terms of a velocity distribution. So, in a measurement, u 1 is measured, u 2 as a function of y is measured, and from these measurements you can find the average values and then substitute in this formula. Okay, so, either you know the average values or you are given the distributions, you can find averages and then estimate the force. So, the other remark is u 2 minus u 1 times h is practically constant, which makes the calculation independent of the choice of the CV. So, will u 2 always be less than u 1? So, for let us say passive objects like a sphere or a cylinder like a chimney. So, all passive objects, you have flow going past the object and it produces a velocity defect. Its velocity downstream is less than the velocity upstream. The difference between the two leaves the sides, but you can imagine active objects. If an object is active, it can draw air from the sides, air comes in from the sides, and the flow going out is more than the flow coming in. In that case, the direction of force is reversed. If u2 is greater than u1, u2 minus u1 is positive. So, force acting on the control volume is positive, force acting on the object is negative, and therefore, the force required to hold the object in place is positive. So, if u2 is greater than u1, then you have a situation where flow is drawn into the control volume, and this elongated 8 is I am just anticipating the use of a propeller which draws air into the control volume and reverses the direction of force. Okay, so let us continue our discussion of flow over a flat plate. So, we construct a control volume above the plate. Now, like a free body diagram, I have recommended showing the control volume separately. Do not mix up the control volume with the object. Do not show them jointly, show them separately. So, now this is 1, this is 2. Now, A B is the solid surface. So, u dot n is 0 here. It may not be readily apparent, but u1 and u2 are not equal, and the difference between the two will leave the side surface, let us call this V3. Okay, so, this dimension is h and A B is let us say W. So, applying mass balance equation, the unit normal on the left plane is to the left, therefore, you will have a negative sign minus u 1 h plus u 2 h plus V 3 W is equal to 0. And then writing the momentum equation, this is the x component momentum equation, f x is equal to rho minus u 1 square h plus u 2 square h minus V 3 W u 1 . Okay, and V 3 W can be written as u 2 h minus u1h minus u2h this last one should be plus. Okay, because V3 and the unit outward drawn normal are in the same direction. V3W is u dot n ds on that surface. So, this again becomes like in the previous example, this is rho u2h multiplied by u2 minus u1. Now, this f x will have, let us look at the force contributions to the control volume. So, there is P 1 here and there is P 2 here. These will contribute to the x component of the force. So, f x can be written as P 1 minus P 2 times h. Then there will be a shear stress distribution on the top surface in the x direction. So, in case you want some assistance on notation, you can always go back to this stress at a point definition, sigma x x, sigma x y. Okay. So, on the top surface, it is sigma y x. Okay. So, if you choose the top surface, as in the previous example, you choose the top surface to be the far field. So, shear stresses will vanish on that surface. So, here you write far field, that will make sigma y x equal to 0. And then there will be a distribution of shear stresses over the lower surface. Why distribution? Because it will appear along the surface. There is no single point where it is going to be applied. It is distributed over the interface of the fluid medium and the solid surface. So, here we keep thinking of Newton's parallel plate experiment. So, the lower surface, in this case it is not that the surface is moving, surface is fixed, but the fluid is moving. So, this you may call, so at the wall, what is the notation we use for shear stress at the wall is tau wall. We use the symbol tau wall plus tau wall times, well, this the way it is shown. As per notation, it is negative times the width. Okay. So, these are the forces acting on the control volume. See, there is no object inside. So, it is only at the boundaries that the forces will appear. Now, you can't simplify it further, but suppose you estimate P 1 and P 2 to be equal. Let us say you have done some experiments and you find that P 1, P 2 they are nearly equal, because it's the flow, the surface is not distorting the flow very much. Suppose you are given this extra information that P 1 is equal to P 2. So, see, based on the momentum equation, you can only come up to this point, you can't simplify it beyond, but with additional knowledge and sort of an estimate. These are called modeling steps. Okay, so, you use your own prior knowledge of the subject and extract more information from the result you have obtained. So, if P 1 is equal to P 2, then so this is an expectation. Then this f x, so you have minus tau wall times h is equal to rho u 2 h times u 2 minus u 1. Okay. So, on the if you transfer the force acting on the control volume to the solid surface, let us say this is the solid surface, this is the wall. So, the force acting on the wall will be equal and opposite. Okay, so, this will be the sign of the force. So, again with reference to Newton's parallel plate experiment, in that experiment you had one wall moving to the right and the force was also acting on it in the same direction. You required a force in that direction to move the plate in that direction, and then a velocity distribution was set up in the gap between the two. So, now here you have a fixed wall and flow is going past the wall. So, indeed you will expect the shear stress to act to the right in this wall. So, fluid force will be directed to the right. So, if that is the case, then it follows that the left hand side will be negative. So, u 2, it follows that u 2 will indeed be less than u 1. Okay. So, this will give you, if u 2 is less than u 1, it will give you tau wall as positive, which means the direction of tau wall is as assumed, and you will have a force acting on the wall that is directed to the right. Okay. It is acting at the wall. Oh, here, sorry. Oh, that is, thank you. Yeah. So, if you apply the governing equations, you come up to this point, and then you can extract more information from it by using your judgment. Okay. Now, while applying your judgment, the choice of the control volume plays a very important role, because one or more of the boundaries can be defined as the far field. Now, because force acting, once you have this far field, then you have a force acting on the control volume equal to force acting on the, or negative of force acting on the object, which is also the negative of force acting on the force required to hold the object in place. Because of the equality of all these forces, in the book they show a control volume that includes the object. So, because those forces are all equal. Now, just for clarity and simplification, let us stick to this approach where you choose a control volume not including the surface. Okay. Just stick to this approach and then do the transfer of information from control volume to the solid surface. So, the book adopts some shortcuts of that type, but let us go through this first principles route. This book also has a formulation in which the control volume is constructed using streamlines. Now, in a streamline is a curve in the flow field to which the velocity vector is tangential. Okay. So, let us say this is the streamline. Then at every point the velocity vector is tangential to it. Okay. So, how do you find such a streamline? We can discuss later, but particularly in steady flow, this streamline can be identified and it is very useful. If the flow is unsteady, it keeps changing from instant to instant. That means the streamline will keep moving, it is no longer. Then you have a moving control volume, it is not very useful. But let us say it is steady flow, if the velocity is tangential, fluid velocity is tangential to that line, how much is the normal velocity component on that surface? 0. Normal velocity is 0. So, and you have u dot n appearing in both mass balance equation and the momentum equation. And we said control volume can be chosen any way you want. So, I may choose this streamline to construct my control volume. So, let us say the object is here and this is another streamline. So, I construct a control volume. This is inflow plane 1, outflow plane 2, and this is the object. So, in this case, so let us say this is now H 1, this is H 2, it is not the same H, it is not a rectangular control volume. Okay. Let us say a curvilinear quadrilateral. The advantage is u dot n is 0. In the previous example where we had a rectangular control volume, some flow was leaving the sides. Now, no flow is leaving the sides. So, here you can write f x. Well, mass balance will give you minus u 1 h 1 plus u 2 h 2 equal to 0. Nothing is leaving the sides, and f x is equal to rho integral, well, I think this you can evaluate the integral. Minus u 1 square h 1 plus u 2 square h 2. So, you have a simpler expression, nothing is leaving the sides. Okay. But you have to choose your streamlines carefully, because they have to be in the far field, otherwise you will get the force acting on the object along with all the forces acting on the respective faces of the control volume. Okay. So, the streamlines again have to be in the far field. If you do that, then you get simpler expressions, but then let us say you fix H 2. If you fix H 2, that will fix H 1. So, or in the other way around. So, in such problems, fix H 2, find H 1 from mass balance equation, and then find forces. So, this is the overall approach. where the calculations are carried out in terms of streamlines. So, on a streamline you can write down u dot n is equal to 0, but the streamline has to be in the far field, otherwise it will experience shear stresses. Let us look at an example. So, this book has a very important application related to flow impinging on a curved surface. This curved surface is like this and flow is impinging on it. This curved surface is called a vane, V-A-N-E. This vane is a very important component of a machine called a turbine, and this jet is usually a liquid jet falling on this vane, creating a force acting on it. So, such a turbine is called a hydraulic turbine. It is a very important application where we can try out our knowledge of mass and momentum equations. So, an idealized form of a vane is a vertical flat plate. This is a vertical flat plate and there is a fluid jet. This is not flow everywhere, now it is a jet. That means, it has a finite size and then it falls on the plate and turns around. So, this is u equal to capital U, and let us say this is A j is the cross sectional area of the jet, and this is a plate held in position, and you want to find the force acting on this surface. So, we want to solve this problem using the integral form or the global version of mass and momentum equations. So, we set up a control volume which includes the fluid phase. So, I am giving you a problem. So, I think the book has solved this problem by including the plate inside the control volume. We do it by excluding the plate. So, our control volume will be like this. This is capital U, cross sectional area is A j. Let us call this. So, this is inflow plane 1, outflow plane 2, outflow plane 3. So, applying mass balance. Okay, now, on this surface normal velocity is 0 because it is a solid surface. Now, these boundaries, they are not solid, they are all liquid surfaces, right. You have a tube and your solid surface, oh, it is not holy season. I used to teach this course the second semester and I would keep referring to holy. Now, I should not do that. This is not that season. So, it is not that you have a jet impingement on a human being, maybe from behind. So, you have a liquid jet coming out, it is not a solid surface, but you can imagine it to be a stream surface or a stream tube, like a streamline. All the flow is along that surface. So, we visualize this surface, this flow is going around and turning this way. It's turning around. So, this is a stream tube. Because it is a stream tube, u dot n is 0, not because it is a solid surface. The vertical surface has u dot n equal to 0 because it is a solid surface. So, minus u a j plus u 2 a 2 plus u 3 a 3 equal to 0. It's mass balance equation, and the momentum equation is force F x is equal to rho minus u square a j plus. Now, the x component of velocity on planes 2 and 3, the flow is completely, it has turned around. So, the x component of forces on planes 2 and 3, x component is 0. So, there are no further terms to be added. So, the force, so this term is entirely negative. So, the force acting on the control volume is to the left. Therefore, the force acting on the object, so if you, this is the vertical surface, is force acting on it is minus f x, which is rho u square a j. This is the force acting on the surface. So, if you do not restrain the surface, it is going to move. Okay. So, if you apply a restraining force, that will be again the same as minus rho u square a j. So, you have to distinguish among these three forces. In the turbine context that we will study on Wednesday, this plate is mounted on a shaft like this. Then there is a jet acting on it. So, that force will then turn this turbine, and then you can see a conversion of force into motion. Okay. The product of the two being generation of power. You can see it as power generation or conversion of kinetic energy of the jet into angular motion of that shaft. There are several ways of seeing the same thing, but force now sets a different object in motion. Okay. But our emphasis is on this part, where you have a fluid jet which generates force acting on a surface. Let us see. So, there are several examples in the book where both components of forces are active. I think in most of the examples. How about that flow past an object? What about the y component of the force? So, here you had an object, and then there was flow going out that way and flow going out with a negative sign, right. There was flow going out this way. So, if you calculated the force acting on the object in that direction, Let us say the object is symmetric, then the flow going out that way and the flow going out this way will be equal, and the force acting on the object in that direction is 0. So, here by and large the force acting on the object is in the x direction. If it is not symmetric, of course, there will be an unbalanced force in the y direction, okay, which also tells you that if you want force in that direction, object has to be unsymmetric. If it is symmetric, they will cancel each other. But in other examples, let us say you have a bend. Let us say there is flow coming in and flow going out. This bend will experience forces in both the x direction and the y direction. So, that we will take up this problem in the next class, and then start our discussion on flow impingement on a curved surface.